Let's take a look at another inequality proof that uses induction. So we like to prove that 2 to the n is less than n factorial for all integers n that are less than or greater than or equal to 4. So for factorial, maybe some of you haven't seen a factorial in a really long time, maybe ever. So when we're thinking about a factorial is we're going to multiply numbers that are less than or equal to it. So for instance, 1 factorial is equal to 1, 2 factorial is equal to 2 times 1, which is 2. 3 factorial, this is 3 times 2 times 1, which is 6. We have 4 factorial, which is 4 times 3 times 2 times 1, which would be equal to 24. 5 factorial, as you would expect, is 5 times 4 times 3 times 2 times 1, which is 120, and so on and so forth. So this is what the factorial function does, is it multiplies a whole bunch of numbers. So if we look at this statement hopefully maybe isn't as trivial as the statement that we just proved. We have to figure out, okay, when I have repeated multiplication, I have exponents. Here's also repeated multiplication. So we'd like to show that this statement is true using induction. So again, we need to have our base case. So we have our proof by induction, our base case. Our base case is the smallest value of n in which this is true for that we're trying to prove, and indeed n equals 4 is where we're starting. So our base case is we're going to let n equal 4. So notice 2 to the 4th, this is equal to 16, and 4 factorial we said was equal to 24. Since 16 is less than 24, our base case is true. So we're able to just work through the arithmetic, see yes indeed, plug in 4 there, great. So now we'll do our induction step. So we will assume this is true for n. So we will assume 2 to the n is less than n factorial for n. We'll prove 2 to the n plus 1 is less than n plus 1 factorial. So we're assuming that this is true for n. We'd like to prove this. Or in other words, I'm trying to assume that this statement is true for n, prove it's true for n plus 1. So now we have to figure out how do I come up with some types of inequalities that will make this true. All right, so if we look at some things, so if we look at this 2 to the n, less than n factorial, again, I like to work with the left-hand side. I like to work with 2 to the n plus 1. How can I make this become that? Well, I just multiply by 2, right? So by multiplying the induction hypothesis by 2, we see that you have 2 to the n plus 1 is less than 2 times n factorial. Okay, that's good. But we're trying to figure out why is this going to be less than n plus 1 factorial. So we think about what does this factorial mean? Again, what n plus 1 factorial is this is going to be n plus 1 times n minus 1 times all of these smaller numbers that we just keep taking out all the integers until we reach 1. So what is the relationship between n factorial and n plus 1 factorial? Well, if we look at this, all of this smaller bits is really n factorial. So n plus 1 factorial is equal to n plus 1 times n factorial. So if I could now argue that 2 is less than n plus 1, well then I can show then that this is going to be less than n plus 1 factorial. So is 2 less than n plus 1? Well, because n is starting at 4, we should see that that is true. So since n is greater than or equal to 4, we see that 2 is going to be less than n plus 1. Right? we know that this is true. So then, hence, 2 times n factorial is going to be less than n plus 1 times n factorial, which is equal to n plus 1 factorial. So therefore, 2 to the n plus 1 is less than n plus 1 factorial. So we have indeed shown that this statement is true for n plus 1. So then by induction, 2 to the n is less than n factorial for all integers n greater than or equal to 4. And that concludes our proof of this inequality.